In this video, we're going to talk about logarithmic functions and their applications. And so a logarithmic function, this is the latest basic function that we are reviewing in this course. These are inverses of your exponential functions. So we've already found that, for instance, the graph of an exponential function looks something like this. All right, this is what an exponential function would look like if it's y equals a to the x. If a is greater than 1, it's an increasing function. It has a horizontal asymptote, so on and so forth. This function is also one-to-one. And so if we were to try to find the inverse of this function, we would interchange x and y. And so we'd get x equals a to the y, and we would try to solve for y. Well, that y is in the exponent, right? And so the only way that we're going to solve for y is to introduce what we call the logarithmic function. The logarithmic function is actually defined as another way to basically write, or this is the way we're defining it, another way to write this exponential expression here. If I wanted to isolate y in this exponential expression here, this is how we do it, all right? If a to y equals x, then y equals the log at base a of x. Notice this a is called your base. It was the base of your exponential function if we were to try to do the inverse. All right, so log at base a of x, we always take the logarithm of some value. That value that we take the logarithm of is actually what a to the y equals, and that is y. This is the definition of a logarithmic function. All right, and again, we read that as y equals log at base a of x. A logarithmic function is the inverse of your exponential function, and it has an input. For your logarithmic function, your input is in the place of this x here, and the output is actually your y. All right, so that we can get used to this, and this relationship allows us to really get used to taking these logarithms, we're going to take look at a few examples. For instance, in part A here, we have log at base 2 of 16. We want to find out what that equals, right? So basically what this is saying, if I want to evaluate this, you can switch into writing this as an exponential expression, and we can say 2 to some power is going to equal 16. Remember, log at base 2, 2 is the thing that we're raising to a power. The logarithm always equals an exponent. And 2 to that base is always going to equal what you take your logarithm of, right? I want to know what power I raise 2 to in order to get 16, and that would be 4. All right, so we can convert it back to an exponential equation, or an exponential, equation, and it'll help us solve this equation. Part B, 16 to what power equals 2? Well, if I take the fourth root of 16, I'd be able to do that. Now, another way to do this is we already know how to solve exponential equations by getting the base to one side, right? So I can put an x here, and I can say, how do I solve 16 to the x equals 2? Using our knowledge from before, we know that if I raise 2 to the fourth power, that's the same thing as 16. So we could write our equation that way. And then when I raise a power to a power, I got 2 to the 4x equals 2. And this is understood to be a first power here. And so now that we have two exponential functions with the same base equaling to each other, and we have an equation, by the one-to-one property, we can set each of our exponents equal to each other, and we'll see that x equals 1/4. All right. But any logarithmic statement is basically you're trying to determine what power you raise your base to in order to get the input of your logarithmic function. So what power in part C, we have log at base 4 of 1. What power do I raise 4 to in order to get a result of 1? All right, and so that is going to be 0. And then part D, what power do I raise 16 to in order to get 16? Well, 16 to the first power is 16. So log at base 16 of 16 equals 1. We do have some special logarithms. We have common logarithms. These are logarithms with base 10. That line is missing there. So we write log at base 10 of x. We drop that 10 subscript, and so it's understood to be there if we don't see log a base on our logarithmic statement. We also have the natural logarithm, excuse me. That's the log at base e. So instead of writing log at base e of x, we're going to write ln of x. Remember, your logarithmic functions have an input value. So log at base 10 by itself means nothing, right? A log of nothing, the letters log means nothing without having an actual input. And so a lot of times you'll see people write these in parentheses to remind us that we always have to have an input here, because ln by itself means nothing. There's two letters. Our log means like a log of wood maybe, by itself. That's what it means, right? But we always have an input in our logarithmic functions, and usually what comes after that logarithm, not including the base, is your input value. All right, and so you'll see sometimes we'll put parentheses here, and you'll see sometimes, well, you'll see sometimes, like in this example here, where we don't necessarily have the parentheses. But remember, there is an input always with the logarithmic statement. All right, and so just to get used to not seeing a base, and we want to be able to evaluate logarithmic expressions that look like this. And so this is the common log of 0.01. Remember, this is base 10, right? So this is asking the question, what power do we raise 10 to in order to get 0.01? Now, if this is hard for you to figure out, remember, you can get the same base on both sides. I'm going to change that to an x and go back to how we solved exponential equations before, right? Well, this is 1 over 100, right? And 1 over 100 is the same thing as 10 to the negative second power, right? And so by our one-to-one property, if these bases are the same and this is a true equation, then the only way for this to remain a true equation is for x to equal -2. So the common log of 0.01 is -2. And then last but not least, for example, 2, we have the ln of e. This is the natural log of e, evaluated at e. Remember, there's understood to be a base e here. So this is like asking the question, what do I raise e to in order to get e? Well, that's e to the first power. You raise e to the first power to get e, all right? All right. And so that is looking at evaluating logarithmic expressions when we're using these special logarithms. These logarithms are special not only because they're base 10 and base e, they're widely used, that's why they're special, but they're both also on your calculator. So I'm going to come here, and I got stuck just now in my thinking. But if you look at your calculator, you have log button, that's going to give you log at base 10, and you have the ln button, that's log at base e. As a hint to what the base is, you can always look at that shift key. The shift key is going to give you the actual exponential function that's related to it. So log at base 10, its inverse is 10 to the x. Ln, its inverse is e, okay? Just so you're aware. All right. One of the things as we continue to work throughout the semester, you want to be able to convert between a logarithmic expression and an exponential expression and vice versa. And so in this example here, we just want to get used to converting or rewriting these things. It's very similar to what we've just been doing. But here I have the log at base 4 of a equals b. I want to write this as an exponential equation, right? An exponential equation. Well, my base here is 4. The exponent is always what your logarithm equals. And then what we're taking the logarithm of is our output when we raise that base to that power. So to convert that to an exponential equation, that's 4 to the b equals a. All right, all we're doing is rewriting it as an exponential equation. We're not solving anything here. All right, in part B, remember we have the common law here, so it's understood to be a base 10. So I get 10 to the second power equals y, okay? So that's my exponential equation. You can simplify that a little bit, but you won't see the exponents anymore. So it's fine if you leave it in that form right there. All right. Example 4, we're going to go the other way. We are starting with exponential equations, and we want to write it as an equivalent logarithm, a logarithmic equation, right? So whatever I'm raising to our power is our base. So I'm going to say log at base 10, and whatever that exponent to that power equals is what we take our logarithm of. So it's going to be log at base 10 of w equals 5. Now, we said that log at base 10 is a special logarithm. It's our common logarithm. So if we don't want to write that 10 there, we don't have 2. It's kind of understood. Almost like when we do the square root of x, that 2 is your index, understood to be 2 is understood to be your index. With the common log, that base 10 is understood to be your base. That 10 is understood to be your base. All right, let's go to part B here. And in this equation, our exponential expression is on our right-hand side, but it's the log at base E of P equals X. Remember, your logarithm always going to equal your exponent. This is your base, and that's what you're taking your logarithm of, right? And so because this is our logarithm at base E, it's our natural logarithm, instead of writing log at base E, we are always going to write ln of P equals X. Too many letters with that E there. All right, so all of this is basically doing the same thing, right? Knowing the relationship that a logarithm and an exponential function are inverses of each other, and the logarithm is created partially so that we'll have a solution to finding the inverse of your logarithmic expressions. Let's talk about the graph, right? Now, we've already said that when two functions are inverses of each other, their graphs are a reflection about the line y equals x, right? And so basically, if this exponential function looks like this, then our logarithmic function should look something like this so that we can have a reflection about our x-axis. But let's look at an example and see if that actually happens. And so we're going to look at the sketch the graph of f of x equals log at base 2 of x. We're going to use its inverse instead of plotting points, all right? And so remember, if I want to find the inverse of a function, right? So we start with the function whose inverse we're interested in. And we interchange x and y. And then we try to solve for y. Well, if I'm going to try to solve this for y, what I'm going to do is I'm going to rewrite this as an exponential equation, right? So my base is 2. My exponent is always what my logarithm equals. And I get my y here, right? So basically, we have y equals 2 to the x. This is our inverse function. And we know how to graph this inverse function here, right? So we plug in, and this is one of our parent functions that we know. We plug in -2, we get negative, sorry. So what I'm going to do in black is I'm going to graph the inverse function, f inverse equals 2 to the x, and I'm going to also label my points. When I plug in -1 for x, I'm going to get 1/2, or 2 to the -1. I get the point 0, 1. I get the point 1, 2, and I get the point 2, 4, excuse me. And so this is f inverse of x equals 2 to the x. And now that I know that relationship between the function and its inverse is the fact that they are reflections about the line y equals x, and I can interchange my x and y coordinates to all of our points, then I can get the point, well, the point -2, 1/4 will be the point 1/4 -2. The point -1, 1/2 is the point 1/2 -1. The point 1, 0 is 0, 1 is 1, 0. I get the point 2, 1. And the point 4, 2. And what we're going to see here, and as this function rolled this should not pass our x-axis here. It's hard for me to draw on this thing. And this should not pass or go across our y-axis here. But this will be considered f of x equals log at base 2 of x. And as you can see, they are reflections about the line y equals x. Here are some properties of this function here. And actually, I'm going to pull this up ever so slightly so that we can see these as well as the graph. And so the domain of this function is the range of your exponential function. Your range of your exponential function was 0 to infinity. So for this basic logarithmic function, this is going to be from, your domain is going to be from 0 to infinity. Now this is log at base a of x. Now what's particular about this a is greater than 1. all right? We had this increasing function, all right? So this goes along, these properties go along with this specific graph here. My range is from negative infinity to infinity, okay? And as I see that my a here, which is my base, is greater than 1, this is an increasing function. If my function, my logarithmic function had a base that was between 0 and 1, it will be a decreasing function. The x-intercept is similar to the y-intercept of its inverse, so it crosses the x-axis at 1, where this one crossed the y-axis at 1. So the x-intercept is 1, 0. It has a vertical asymptote. It doesn't have a horizontal asymptote. Its inverse does. And then all of these functions are 1, 2, 1. All right. So these are some of the properties of logarithmic functions that have an a that's greater than 1. The logarithmic function that has an a, so if I had a logarithmic function like log at base 1/2 of x, the graph is going to look something like that, and it's going to be a decreasing function, but we're still going to have a vertical asymptote, so on and so forth. All right. Now, these graphs here with these properties are the basic graphs of logarithmic functions, and so we'll add that to our family, our library of functions as a parent function. But we can use transformations to get more complicated logarithmic functions. All right, remember this gives us the horizontal shift. This gives us a vertical shift. And then this value here gives us a reflection about the x-axis. And it can give us a vertical shift if that number is different from 1 or negative 1. All right. And so remember that those transformations always apply to all functions. All right. What we want to do lastly is determine how we can solve logarithmic equations. There are actually multiple ways that we can do this, actually 2 ways that we're going to review. One way is to do what we've been doing before in the examples above here. What we've done was we've gone from an exponential equation to a logarithmic equation, right? And in these examples, we went from a logarithmic equation to an exponential equation, right? So sometimes we can convert from a logarithmic equation to an exponential equation, and it's something that we can solve, all right? And so we can use that property in order to help us solve logarithmic functions, equations, or we can use the one-to-one property, all right? And we're going to see an example of each of these, and we'll talk about when you want to use which of the two, all right? And so let's look at this example. Notice the setup of this. I have a logarithm just on one side of my equation, and I have a constant on the other side of the equation. When that is the case, I'm going to try to use this method here. So a log on one side and constant on other side, okay? Then this is a perfect setup to rewriting this as an exponential equation and then solving the resulting exponential equation, all right? For instance, I have log at base ax of 16 equals 4. Well, if I write that as an exponential equation, I get x to the 4th power equals 16, all right? Now, to solve this equation, we have to solve for x. We have to undo the 4th power, and so one way to do that is to do the 4th root. All right, when we undo something by doing the 4th root, so I'm taking the 4th root of both sides. Since we're using an even number, this is actually equal to an absolute value. And when we usually say that this equals an absolute value, we put on a plus or minus. The 4th root of 16 is 2. All right, so we get x equals plus or minus 2. One of the things that you always have to check when you're solving logarithmic equations is that your solution is in fact the solution. We said, and one of the reasons why we have to check is because the domain of logarithmic functions is not all real numbers. That means you can't input into a logarithmic function a negative number. The domain is from 0 to infinity. It's very similar to square root functions, but logarithmic functions are even more restrictive because you can't even plug in 0 into a logarithmic function. All right. Not only that, depending on where our variable is, because this is the inverse of a exponential function, and the base, that a, which is our base of our exponential function and the base of our logarithmic function, has to be a positive number. Depending on where our variable is, we need to make sure that that is always a positive number. So if I look in this example here, my x is in this base. My base can never be a negative number. And so since I have x equals plus or minus 2, that minus 2 is not a part of my solution. So my only solution set is x equals 2. All right, let's go to part B. In part B, we have the log at base 3 of 2x equals the log at base 3 of 24 minus x squared. Notice I have logarithms on both sides of my equation. And the logs have the same base on both sides. All right, this is probably not the most grammatically correct way to say this, but my logarithmic expressions show up on both sides and they have the same base. All right, this is a perfect setup for the one-to-one property, because the one-to-one property when we were dealing with exponential functions was, oh, well, if I have a to the x1 equals a to the x2, since this is a one-to-one function, I can just set my exponents equal to each other, and that's going to give me my logarithmic expression. Well, the same thing happens here. I have a log at base 3 of 2x, and that equals a log at base 3 of 24 minus x squared. If this is a true logarithmic equation, then by the one-to-one property, that's one-to-one, I can remove those logarithmic expressions and just set the arguments or the inputs of my logarithms equal to each other. And now this becomes a quadratic equation. So I'm going to get everything on one side and 0 on the other. Since I don't want my x squared to be negative, I'm going to add x squared to both sides and subtract 24 from both sides. And then I'm going to solve my equation. Two numbers that multiply to give me 24, but add up to a positive 2. Set each of those factors equal to 0. So I get x equals 4, x equals negative 6. Remember, we need to check our solutions. What I do when I check my solutions is I plug in the values into my original equation, right? I want to plug it in to make sure that I don't get a negative value, because if I get a negative value in the input of my logarithmic expression, then I'm going to get no solution. So or something that's undefined, right? Because I can't take the logarithm of a negative number. So let's plug in 4. When I plug in 4 here, I get 2 times 4, which is 8, so that is fine. When I plug in 4 here, I get 16. 24 minus 16 is 8. Both sides are equal. I'm good to go there. Now, I didn't necessarily, since I'm confident in the work that I did, I didn't necessarily have to check that both sides was log at base 3 of 8. Right? What I wanted to really check to see if I got a negative number, right? For instance, when I try to plug in negative 6 into this side, I'm going to get log at base 3 of negative 12. I immediately know that that's not going to be a solution because that is negative. And so my only solution here is x equals 4. And so always, 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 always check your solutions, because sometimes when you have functions within the logarithmic functions, things happen, especially when you got them squared and all that stuff, that may make things a little weird. Last but not least, now that we have this, we have a method that allows us to solve more equations. All right. Now, the logarithm is going to be very, very helpful in allowing us to solve exponential equations in even a different way. All right. And so we're going to look at this example here to help us figure that out. How long does it take for a deposit of $1,000 to double at 8% compounded continuously? All right. Well, when I see that my interest is compounded continuously, then I automatically know that this is my formula that I've already memorized, because we've already memorized this formula. And I think in our notes, we use A, or A sub t, right? And so I want to know how long it takes for a deposit of $1,000. So that's my P naught at 8%. So that's 0.08. I don't know how long it is, and I want to find that T, right? But I know that doubling means twice the amount that I started with. And so if I want to solve this equation, I've got to solve for t. Well, for me to solve for t, I need to isolate the t. Well, the first thing that has it unisolated is for me to get rid of that 1,000. So I'm going to divide both sides by 1,000, and I get 2 equals e to the 0.08t. And now I want to be able to solve this equation here. Well, what I know here is that t is my exponent. And so what I'm going to do is I'm going to use the fact that logarithms and exponential functions are inverses of each other. And so I could rewrite an exponential expression as a logarithmic expression and vice versa. For instance, if I have this exponential expression here. My base is e, this logarithm equals 2, and that exponent is what your logarithm always equals. I'm basically going back to the examples where we rewrite a logarithmic expression as an exponential expression. Actually, we did this way here. I take my, basically this here. It's following this example here. I have the log at base e of p equals x, right? So I did the log at base e of 2 because that's what your exponential equation to a expression to a power equals. And that logarithmic expression is going to equal your exponent. Now we know that ln log at base e is the natural log function. We can divide both sides by 0.08. And so we get t equals that natural log of 2 divided by 0.08. And just so that we can get used to or familiar with the calculator, let's look at putting this in our calculator. And so here, I'm going to do the natural log ln of 2 divided by 0.08, and I get 8.664, 8.664. And when we're talking about the finance, that's called years. All right. And this is one way that we're going to use logarithms in order to help us solve exponential equations, because this, my friends, is an exponential equation. But this concludes this video. I'll see you during the next one.